and a damp natural frequency kind of extending out. What we're going to start taking a look at now is an idea of how do we use this understanding to actually figure out what's going on inside of a system. So there's essentially one thing. We've noticed the denominator, what we call the characteristic equation of our Laplace transform, tells us about the behavior of the system. So we've determined that this concept of what we call a pole is crucial to understanding how the system behaves. Now, what happens if your poles, instead of being fixed, what if they're variable? Right? What if, as you adjust some gain parameter, your poles move? You could then achieve different types of behavior based on what you set the value for. This is one of the basic ideas behind control systems. Now, we're going to take a look at kind of the simplest system that goes in here. And this is what's usually typically done in undergrad control classes, where we kind of assume a particular form of what the control is going to take. When you move on to graduate control things, you don't assume any particular natural form to it other than like linear or quadratic cost or things of this sort, and you find whatever the optimal parameters are for this. But this is a good kind of first cut on it as it goes. So what we're going to imagine is that we have reduced our system down to something that looks like this. So we'll assume we've got something of this form. Okay? I can't in general get anything to this form. Imagine G of S is your basic, this is what you're trying to control. This is your plant. You'll also see these are fairly typical letters, G, H. You will sometimes see for some people they add in an F over here. I'm going to drop that in a sec. But the reason for people doing this, if you think of G, this is your plant. H, this is what you have measured from the outputs and you're using to correct. And F is some idea of how the inputs are controlled. All right, so the FGH is one of the common letter patterns you will see. So there's some groups of schools that use those. You'll see other people who like to use the A, B, C, D letter pattern, where A is your system and B is your inputs, C is your measurement, and D is how the inputs affect the measurements as it goes on. So you also see those ones.
So you said H was the...
This is measurement. So think of this as the output. This is your plant. This is what you're trying to control. Remember we had all that block diagram algebra? So imagine for a second you haven't put any control on it. You just reduced what am I dealing with, and you reduced it to a single block. Okay?
Right.
Now from that, there's some inputs to your plant and some outputs from your plant. I have to measure those outputs. And I might not be measuring purely just one. I might measure some combination of them. Right? And it depends on what I have available to me. So in some sense, H is telling you how were you doing the measurements. And it can also contain some of the control law for the feedback as it goes. But usually we like to use this one for your feedback control. Because then it knows what was the input, what were you trying to get it to do, plus what is it doing. And if it knows what it was trying to do and what it was doing, it can do a better job for control in that sense. And we can show that in the end it doesn't make a huge bit of difference actually. I can do it, but conceptually it kind of seems nice, and so this is how people originally set them up. Now for us, I'm going to ignore that part of it, and we'll just say whatever the output is, we just call that, some target level I'm trying to achieve, and I've got some output Y. But we're not really as concerned with these at the moment. What we're trying to do is figure out what's going on inside here. Fair enough?
Yeah.
Now, for this type of a system, right, so this is, and I should have a minus there because I'm going to be very clear who I'm subtracting, right? Negative feedback. We pretty much always do negative feedback. All right, so we did this maybe one or two times ago, how we reduce these blocks. Can anybody tell me what the transfer function for this system is?
K times G of S.
Okay, so on top I've got K times G of S.
Over 1 plus K times G of S times H of S.
Yes. Very good. All right, so usually this picture goes aside from, you can immediately look at this. Just think for 1 sec on here. From R to Y, whatever's in here along the top line, directly proportional. So directly proportional is going to be whatever's here.
Okay.
And it's going to be inversely proportional, you know, to 1 plus the net thing coming around.
So 1 plus the loop is the denominator,
Yeah.
and just whatever's in the straight line.
And whatever's on top goes on top.
Okay.
So that's kind of the quick, easy way to write it. Now, if you didn't remember that, remember you could put something in here and I could call this X, right? And we could say X equals R, you know, minus, and then I take this and it's H times G times K times X. Bring X all to the other side and that will give you the denominator and divide through, and that gave me X, and then I have to multiply by KG to get Y. Fair enough?
Yeah.
So you could solve algebraically and get this, but at a certain point you want to get comfortable where you don't have to always have to go back to basic principles to solve. Though you can. If you ever forget, by all means, go back to whatever's going to help you to get the answer. Good?
Mm-hmm.
All right, so the behavior of this system now with a set of observations and a control that's in here is going to be given by the characteristic equation, which is the bottom. So this is what we call our characteristic equation. Anybody else know when we use the term characteristic equation?
How many different equations?
Yeah, so in differential equations, where does it come up?
Group holes.
Where you get eigenvalues. Eigenvalues are given by the characteristic equation of a matrix. It's not an accident. They are the same thing. If you were to write this in matrix form, you know, what you get here will give you the eigenvalues for that system. So this is not a case of overloading. This is a case of correctly using the term. So you hopefully will get some insight off of those. If you're not familiar with it, don't worry about it. Okay, so what we're concerned with is when this goes to 0. That's when we have poles. So therefore, the equation we're worried about is when the denominator, I'm going to drop the S that's in there, when the denominator is equal to 0. Fair? That's the equation that we call the characteristic equation. It says, where are the poles? Remember, the poles determine what the behavior was. All right, so we will now break this into 2 different sub-equations that we're going to satisfy. The reason why we do this is in a complex plane, and it's kind of difficult to deal with real and imaginary parts and everything else. And it turns out the real and imaginary parts aren't the biggest thing that are of concern to us. What matters most is actually in polar coordinates. When we go to polar coordinates, we're concerned with magnitude and phase.
Right.
Phase is your angle, magnitude is the radius. So we're going to ask what is the magnitude and phase of this equation. But to do that, we're going to slightly rewrite this equation. This becomes K, G, H equals -1. It's not a major rewrite, but now to figure out magnitude and phase, it's a much easier thing to do. Well, to figure out the magnitude, I just take the magnitude of both sides. That's the absolute value since these are scalars. So that means the absolute value of K, G, H has to equal 1. This one I can't do much else than tell you take the absolute value. But this side, absolute value of -1 is trivial. So this is the magnitude equation. The phase equation, so you can think of this as your radius, and this is your angle. The phase of this, again, I have to find out the angle of KGH. But that's equal to, what's the angle of -1?
180.
That's 180, so it's pi. But isn't it also 3 pi
Yeah. Yeah.
and 5 pi?
Okay.
What about minus pi?
Yes.
Okay,
absolute
but it's not
value.
k pi.
Well, not in K in the sense of that, but any inch.
Okay, so you have to actually really say this is 2k plus 1 times pi.
Oh,
And now you can stick k in for all integers.
So K is kind of just the iteration?
Well, this gives you the idea of I can keep wrapping around
Okay.
as you're going on. I mean, if you think about here's my plane and here's the -1 point, I can either go at radius 1, pi, or I can go like 1.5 times around, or I could have gone minus, right? It just tells you how many times you wrap around.
but I think that the K in the actual diagram is what we're concerned with. So that
Oh.
is actually a scaling
So-
thing, or? Okay, so
It's not that
making
K,
sure, just
right?
Okay.
Sorry about that. All right, so we tend to abusively overload this
I was just
as it
thinking,
goes
like,
on.
what is
Technically, when most people write these, they make this a capital K.
Gotcha.
So that way, when we use lowercase k someplace else, you know they're different because the case is different.
Right.
course.
But it doesn't look that different in my handwriting because honestly, it really isn't that different. But I put those little kind of serifs on the end just to let you know it's a capital letter.
Yeah.
But I'm going to rapidly drop that because, well, I'm lazy. So, and you just have to kind of know what's going on. So this is just n is an element of the integers. Right? And I could actually say if I wanted to, for all or for any of them. Fair enough? Right. So these are the two conditions from which we actually develop all the rules of how to plot what's called a root locus. A locus is a group of things kind of put together that are, connected by a common parameter, and it is of the roots of this equation. There's some basic things that come out of what's going to go on here. And we'll try to draw a few of these out in the first place as some basic principles, and then we'll start talking about how you can actually plot these, and then why the heck you care.
Cool.
All right?
Doctor,
Yeah.
do you think we'll have enough time to go from, say, having a Laplace transformed equation to drawing out the diagram to writing out the transpose function?
Well, that's what we're talking how to draw. We're talking about how to draw this. Do you mean how to actually write one of these things from
From the Laplace transform to come up with like the K, G of S, H of S equation? Or the
Well, everything we've done up till now was how to get G,
Okay. Okay.
right?
Yeah.
Do we all agree with that? And we have done some examples of that.
Yeah.
So, I mean, I can do more of those if you want.
Oh no,
We do as many as you want as it goes. Remember the basic trick of this one, we had two basic steps we did. Right? Step number 1 was you kind of break things up into these nice little things to make a picture of what it, and then in each box you have some simple descriptor of what's going on in that box. That's a differential equation, describes what's happening. It could be, a spring mass, whatever it is, right? You have a differential equation that describes it. We take the Laplace transform of those blocks, and then we use the block diagram algebra to combine them together to get a big G. All right? K, we're going to find by what we're doing today.
Okay.
H is the same exact thing applied to however you're observing this. So you can also take a look at if I've got a measuring system,
Okay.
right? Like I've got a camera, and there might be some delays from when the picture is taken, right? So now we've got a shift in the time axis, and you could walk down the line with every property that's built in there. I can make a Laplace transform of it. The most common thing that is actually done is what's called unity gain negative feedback, where H of S equals 1. You assume you can actually see the real system, and therefore you measure every output that's there, right, rather than some weighted combination that goes on. So that's probably the most common one people talk about. In reality, there's usually delays and other stuff in your instruments as it goes on. And anybody who's ever tried to use like the line followers or things like that knows as your batteries change, your sensitivity changes, right? So the gain on your measurement changes with voltage as it goes on. So a lot of your sensors vary. We can actually account for that inside your system. Right? So rather than you having it, if you've ever had to kind of tune it by hand, which is what you have to do right at the very beginning, having a thing where you can just automatically describe this is how it behaves, and then have the system adjust its own gain, to keep it up, I mean, is a much nicer feature as it goes on. But I mean, we could go through a full example if you want to on that.
Maybe after. we talk
Okay.
about it.
But I want you to keep an idea where this whole thing came from. And then really what we do is just multiply it together, and now let's see what we can do with it and see how it behaves. Okay. So far, so good?
Yeah.
Okay. Now remember when we got these, like for instance, when we got G, it was a bunch of basically a ratio of two polynomials. We had something, once we had factored it, looked like S plus, 0, first 0 times S plus some second 0, all over a bunch of poles that we had factored. I'll just do a simple case where they were all nice little discrete poles. Realize that some of these poles could actually be complex conjugates of each other.
Yeah.
In which case you get oscillations and stuff, but what do I care about that? Huh? So far so good?
Yeah.
So this is what your G looks like. And maybe when you multiply by H, you've added something else in. Maybe it adds some new things. So you end up with, maybe like some Z2 and some extra poles. Whenever it ends up, right? Once I multiply them through, right? So I had my G times my H, but now they're all blobbed together. I multiply by a K, right? And this gives me what is my KGH. Fair enough? Mm-hmm. Now there's a few things I need to kind of define for you first. First off, the top here, we call the numerator, and this is the denominator. Nothing new other than note, we will sometimes actually refer to those because there are some neat things that happen as a result of it. Okay?
Is there a specific
So
reason
the
is there a specific reason we're ignoring a K in the numerator?
yeah, because K is usually what we're trying to find.
Okay.
Yeah, and I can pull K out. And I could really call it 1 over K0 if I wanted, and I could have stuck it with the denominator. So it's kind of like its own little beast, right? So, and that's the thing I'm adjusting, so it's just a scalar. So it's no biggie to kind of deal with it and move around.
Cool.
Yeah, I mean, very good question. If you have questions like that, this is where, I believe the book actually shows some of this, and usually there's tons of these things online. What I really want to do is try to get you to understand some of the big ideas you're trying to do and why they matter, how you'll use them. Okay, so now we've got kind of these numerators and denominators. If you look at this, I've got a certain number of zeros. I've got, in this case, 3 of them. Mm-hmm. But let me just call the number of zeros, I'm just going to call Z. Right? So if it has no subscript, it's just telling you how many there were. Okay, so in this case, Z equals 3. Similarly, the number of poles, P. Fair enough? Mm-hmm. All right. Now, if you consider this equation, 1 plus KGH equals 0. If I multiplied through by D of S, you would end up with, so this equation, multiply through by D of S. So D of S times it. I would end up with D of S plus K N of S equals 0. All right? Yes? You might be wondering, why the heck do I care about this? But you'll see in one quick sec. Right? Let's imagine that I were to initially set my gain, to 0. Right? This describes the poles of the system. So where would the poles of the system be?
DS.
It'd be DS. It would be whatever the poles of this system is. Right? What if I, on the other hand, started taking K and I just tweaked K as high up as I could? I started letting K run to infinity. What's going to happen?
swamp out the other thing.
Yeah, this one, as this starts going to infinity, right, I could just do 1 over k. It's not 0, so I could divide by it, right? So I would end up with a 1 over k and just a 1 here, so this term as it k runs to infinity would just disappear. So all of your poles would run to the numerator, which are the 0. So it starts, we call these the open loop poles. We call these the open loop zeros. So your root locus is going to be made up of things that start here, and I'll have 1 for each of them. And they will run from here to there. Now, does anybody see a little problem with that? I mean, clearly that's what happens, right? I mean, we just showed real simply that basic behavior goes on. However, how many do I have here?
4.
How many up here?
3.
You see the problem? Where does that extra 1 go? So they either have to go to the zeros, or they have to run off to infinity. Because the ones that don't end up going to zeros end up blowing up. So they just run off to infinity. And we can calculate the angle that they will go off to. This is why it's kind of nice to have the different parameters for them. So far, so good? It makes sense, the basic idea?
So you're always, if you have all 3 of the zeros in the top, you'll only have 3 zeros in the bottom. One of them will go off to infinity in the bottom?
Okay, so one of these will have to run off towards infinity.
Right, okay, good.
So let's think about it. Let's plot these for a second, just so we can pictorially get an idea of what I'm talking about here. So if it's going to be stable, where do the poles have to be?
Left-hand side.
Left-hand side. We've already talked about that. So let's say I just, for the sake of argument, I had a couple poles here, and maybe I had a complex conjugate pair out of my 4 poles. Good? Mm-hmm. Now, I've got a bunch of zeros. Now, since we mentioned the fact that if k runs to infinity, the characteristic equation's poles, or the roots, which are going to be the poles of the system, will start going to the numerator, the zeros. So if my gain is set high enough, for stability, where do the zeros have to be? They're also now functioning like poles, aren't they?
Yeah.
And poles to be stable have to be left-hand side of the plane.
Okay.
Right? So if you have any zeros on the right-hand side of the plane, you might start out stable, but as you adjust your gain, it can go unstable. And this will often happen to people. It'll be very stable at the beginning, and then it'll all of a sudden go unstable. And that is telling you that you have some zero that's outside there, most likely. There is a chance it can just kind of bulge in and then pop back to stable again. But in general, you're going to be dealing with something where your zeros are on the right-hand side. So we want them on the left. That's an ideally good situation. Okay? Mm-hmm. So let's assume for the sake of argument that I've got, let's say, a couple ones here, and let's say, do we want a complicated or an easy one?
Complicated.
Complicated? Okay. So I'll make a complicated root locus here.
It would have been easy if all of those ones were on
It would have
the
been
same
easy
side.
if I had taken this and stuck it here.
Oh.
So this is a complicated root locus. The 0 there would be an easy root locus. Let me show you the easy root locus first, and then I'll show you the complicated one. You can see why it becomes complicated.
Yeah, I want to know why.
Okay, so let me start with the easy one then, and remind me to come back to this one, because it's kind of cool what happens in that case. All right, so we'll take this as our spot. Fair enough? Mm-hmm. Okay, so when we're looking at this, we said everything starts, we've got root locus, which means it's starting at these poles, and I got 4 of them. So if I were to just adjust k a little tiny bit, it would be a weighted average of these and these. Right? So they would just shift a little. So they would move from where they're at a tiny little bit as you adjusted k. Okay. So I'll show you why it goes this particular direction.
I
What?
don't know why they're moving it all. I think you lost me a minute ago.
Okay, so we're taking a look at this equation, which is the characteristic,
Right.
and I stuck its numerator over denominator. So we said that what I have is 1 plus k times the numerator over the denominator has to equal 0.
Right.
And I multiplied by the denominator and I got that.
Right. I got it.
Okay. So, and we said k is an adjustable parameter.
Right.
You pick it. So if I pick k equals 0, you have this equation.
Right.
D of s equals 0. That describes the characteristic equation. That describes where the closed loop poles are. All right, because remember, k is my gain that closes the loop. So if we set k to be equal to 0, you effectively just have, you are starting at the actual poles. The poles of your system is the poles of your open loop system without closing it. So in other words, when you close the system up but you have very little feedback at all, it behaves almost like it's open loop, as if you didn't have feedback. Make sense so far?
I don't see why the poles are moving.
Well, the poles are moving because so far right now I've just told you why they start at that point. Now, change k slightly.
Didn't have to
So
do some other.
let's just actually write it out. Right? I've got s plus p0 times s plus p1. I'm just going to do a real simple small one as it's going on, plus k times s plus z0. Fair enough, just a real small one. That has to equal 0. If I now wanted to factor this to find out where are the actual roots of the system for any value of k, I could multiply through, and I would find out I get s squared plus p1 plus p0 plus k times s plus, and then I've got p0 plus p1, or sorry, p0, p1 multiplied plus k z0. And so therefore, the poles, which are those roots, are going to be equal to minus b plus or minus the square root of b squared minus 4ac, 4ac do my z small, my 0 big. Okay. All over 2a. So the poles of this particular system are now here. As you change k, the poles change
So we're
because k is part of it.
comparing poles of 1 plus kth to kth.
So what we're really trying to ask at this point is, could I theoretically take this right here and just solve for every value of k and plot them? Could I?
Do it on top.
Of
Yeah.
course I could. You would get the root locus. Okay? So now the question is, instead of having to solve this equation for every value of k, which is obviously non-trivial, is there some way I can do it without having to solve that equation?
And that's by looking at the zeros and poles.
Yeah, that's why we're trying to say, hey look, and remember I told you shortcuts to plotting, we can sketch a plot. We need to know, where does it start, where does it end, what's the angles, does it do anything interesting in between, when does it cross axes, stuff like that. These become interesting points. So that's things we want to find out, and all we're going to do is sketch them. And it turns out all you need is a sketch to figure out what's going on. You don't need to plot it for all values of k. Could you plot it for all values of k? Theoretically. However, this equation works great when my highest power is s squared. What happens when it's s to the 10th? There is no solution that's closed form. So now you have to do it numerically, right? Which means I have to do an iterative process for an infinite number of points, or infinite values of k. Okay, so you've got a slow process to begin with, and you've got to do it, a ton of times and interpolate. This gets really ugly really fast. So this method, which I would call the brute force method, just stick it in and solve it, theoretically would work, but it's just impractical. And remember, what's the one thing we really want to find out from these graphs? We want to find out, is it on the left-hand side? Right? And remember, if it's really close, right, the imaginary axis itself, is that stable, unstable, or something else? It's metastable. It's kind of something else, which means things really close to the left-hand side, right, are pretty close to metastable, aren't they?
Yeah.
So they have a very slow response. So not only do we want to make sure that it's in the left-hand side of the plane, we want to make sure it's to the left of some boundary position. Right? We don't want it to oscillate too much either, do we? And we said oscillatory behavior had to do with the angle it was relative to the origin, so we can kind of draw out some area. These are lines of constant damping factor. So we say, hey, look, I don't want to be over here, and I don't want to be over here. It kind of snubs the nose off this, right? And so I got to make sure at what value of k do all of my roots lie within this funny little region. Right? Does that make sense as why I want to do this thing?
Yeah.
So if you can kind of sketch a plot, and from that plot you can find out what value of k it was, without having to plot everything exactly, guess and check. I mean, you could guess and check until it worked. Right? But I submit to you it would be easier just to do it this way. And since we do this kind of thing all the time, we've established some rules on how to plot a good enough plot. Now, if you go online, you will find there will be dozens of rules that you can get in there. I'm only going to give you what I think are the most useful to sketch as it goes on. And if you need more funny details, you can of course go in and check up more rules. But these basic ones will be what you need to kind of solve your standard systems as it goes. That makes sense why we're trying to do this and kind of what's happening a little better. I mean, by all means, this is, most of you had not done a lot of stuff with complex numbers to begin with, and now we're plotting, changing functions with multiple roots moving in the complex plane. I understand it's a jump, right? But it's a jump that saves you a lot of trouble. This is your alternative, right? Your alternative is pound through just a tremendous amount of work that your computer may or may not be able to get you a decent solution on. Good?
So the root locus is pretty much a sketch of where the system remains stable.
We are plotting the poles.
Okay.
Where are the poles in the closed loop system for a particular value of k? And since k changes, you'll get it not just individual points, you'll get an entire continuous lines, different branches. I have 4 poles. Poles are conserved. Right? So to conservation of mass energy, you can add conservation of poles. We do actually conserve our poles. Poles are not created or destroyed. This is actually a fundamental theorem of linear algebra. They are roots of a function, and they cannot just go away. So this is where I was commenting, if I've got 4 here and I said they go to these 3, you have to ask the question, where did the extra one go? This is why I was saying it had to kind of run off to infinity. So far, so good? Is it okay if I kind of erase my keep out zones? To put the X's back into. So it looks something like that. And so, now some features about this. If you notice, I drew this symmetric about the real axis, right?
Yeah.
And as I started moving them, they stayed symmetric about the real axis. Why? You got any reason why this might be the case?
They're complex conjugates.
Yeah, I wanted to keep complex conjugates. Why do I want to keep complex conjugates?
Canceling?
When you multiply two complex conjugates, you get a
Real number.
real number. Your net function has a real output. So somehow, through all this stuff in the complex plane, the imaginary part had better cancel out. Okay? We can work with imaginary parts in the calculation, but the output had better be real. Because that requirement that the output has to be real, I have to maintain complex conjugates, which means it must be symmetric about the real axis. So you really only have to draw half of it, and you get the other half by mirror. Okay? And we've already made the statement that things start at the poles and go to the zeros. Now, as I kept adjusting K on this, I'm going to use the rules without telling them to you yet, and just kind of draw it, and then I'll show you why it works. All right? As it keeps going, these are going to keep coming, and they will eventually come together right between these two zeros. And then they will bump into each other for a brief second, and one will go this way and the other will go that way, ending up at those two. This one is going to just keep on going right till it hits here, and this one's going to keep on going, running off to infinity. So that's what this particular graph is going to look like. I will show you the rules in a sec. Now, I made a comment that I could make a much more complicated one by just flipping the order of these two. Here's why it becomes more complicated.
Because you have two poles that are going to smack into each other.
Very good. So I have something that looks like this now. These ones are going to do just what they did before. Slightly different angle to them, but I'm not going to worry too much about it. So it's going to come down, split off, go there. These two are going to move towards each other now until they hit. And then they're going to bounce off. They're then going to come around. They have to end up here. So they have to always stay as pairs, so they're going to have to come back over. One will go here and the other will go down. That's why it's slightly more complicated. Okay, now, how do I know that? That's where the rules come in handy. So the first one uses this, the angle property. Let's just consider the real axis. Now what that angle property is saying, if I consider some point that's along here, and I measure the angles between this to whatever I want, right? Here to here, this to this one, right? So on and so forth, to each one of these as they're going through, right? Here all the way around until I hit this one. That it had better be the sum of all those angles. It better add up to 2n plus 1 times pi. Because that's the requirement. Anything on the root locus has to satisfy the sum of all the angles to the poles and zeros have to end up giving you pi. Now, because of the way that we ended up calculating this, remember the numerator and the denominator comes out, we end up getting the zeros minus the poles. You could technically do it the other way around if you really wanted to. But the standard way, if you write it on the left, you end up with zeros minus poles, plus pi, just to keep it nice and pretty. It has to end up giving you this satisfaction value. Right? So when you go on to here, this one right here and this one right here ends up giving you the same angle.
Yeah.
But since we measure from this axis, this one plus that one is the same as this one plus that one. Now, so they add up to be a 2 pi.
Yeah.
Right? And then we end up getting, your poles minus your zeros as it goes on. If you count them, by going through that, as long as you have an odd number of them, you will end up having that you have the satisfaction of this requirement, that you have pi. because this is just requiring an odd number. So what it really is saying is, you better have an odd number of them to your right. That basically makes sense?
Yeah.
Right? I mean, it's really just satisfying an odd number here. Anything off-axis cancels. So they just go away. So all you have to worry about is the ones on the real line. As long as you have an odd number to your right, you have satisfied this requirement. Good? Okay, so, you know, since it's what we end up with is pi plus the sum of these, and these are all zeros. Anything to your left is going to add, you know, pi's to them. So away we go. So what we want to make sure is anything to our right has added, we have an odd number of them. Or otherwise said, you have to be to the left of an odd number. So I just go count them. This is my first one, so this has a segment. This is number 2, so there's no segment. This is number 3, there must be a segment. This is number 4, so there's no segment. This is number 5, so there must be a segment. That make sense?
Yeah.
So now I figured out how to plot the real axis trivially. This is why I said this split up actually makes it really nice and easy for you. So far, so good?
Could you run that one more time, please?
So the requirement is we need to have that kind of odd number. So if as long as there's an odd number on there to my right, I satisfy the angle requirement. Yay?
Yes.
Right? And we have that angle requirement because we need this to equal -1, which is saying the angle has to equal pi. Okay, so all I have to do is, once I have my zeros along here, remember anything off axis is going to cancel each other. So I don't have to even worry about those. So I just make sure, since this is the first one, right? This is the segment to the right of no pole. So we call that even, so boom, it's out of there. This is 1, right? So now I'm to the left, which means there's 1 0 to my right. I'm to the left of an odd number of poles. This is true, there's only 1, poles are zeros. So this has to have a segment to the root locus. I don't know where it came from yet. I just know it has to be there. And since it's between 2 zeros, it's got to come from some nearby poles. Okay? So far, so good?
Yes.
At this point, if I'm looking at this little segment right in here, there's 1, 2 to its right. Well, there's no segment if there's 2 things to my right.
Okay.
Over and done with, right? So that one cannot have a segment. When I'm right here, I've got 1, 2, 3 things to my right. It's an odd number. It satisfies the angle requirement. I'm golden. So there must be a segment here. When you go to here, there is 4 to the right. 1, 2, 3, 4. Therefore, there cannot be a segment there. This is the last segment there is. And there's 5 to my right. So
One's up.
there must be a segment there. And it runs off to infinity.
Now, the odd rule, that's only because we have a pi.
That's because I have to have this -1.
Yeah. So if that came out to be a positive one, somehow we need to have an even number.
Well, the way you would run into the challenge is if instead of having negative feedback, you had positive feedback.
Okay.
You would have flipped the sign here, which means you would need your angle to be equal to 0 or multiples of 2 pi. So you'd need an even.
So on negative
Okay.
feedback, we need an odd.
So positive feedback, you'd have to go there. But realize what that means, and this is why we don't like positive feedback. If you were doing positive feedback, I got different colors than me. Let me take advantage of this. That would mean your segments would be here, right? Here,
And the right half of the
and here. Do you notice the problem?
on
the
the
right half of the line.
You've always got a segment that's going to be lying over in the bad zone.
Yeah.
You cannot avoid it. So if you do positive feedback, for any sufficiently large gain, your system goes unstable.
Is there a scenario where we want that?
Where you want things to blow up. Well, if you want things, I mentioned a real easy ability to turn things like that, something that you want to change quickly, is best done unstable. But then you've got to rapidly bring it back in. So,
So, is there a practical application to positive feedback?
it's very, very, very rarely used.
Okay.
Okay? You had better really know what you're doing before you call for positive feedback. So theoretically, could you make such a thing? Yes. Could I imagine some situation where I want something to go just a little bit unstable? Yeah, potentially. But nobody establishes rules for designing these, because we don't want you to design it unless you really, really, really know what you are doing, and therefore don't need the rules. Right? If you need to look up rules, you shouldn't do it. That really would be my kind of advice to you on this. Anytime you go to something dangerous, you had better know it so well that you are not walking in a, what do I do next? Look for next formula. Okay, check off. Right? Because you're just not familiar enough with it to be safe in that type of a zone.
I guess that 22 has the equivalent of positive feedback.
There are aircraft that will deliberately push themselves unstable, but I can actually push myself unstable even with negative feedback. I can force a loop to go just slightly unstable.
They force an
You know.
unstable.
Yes. So there are different ways to force it. You can force it with negative feedback. It's really easy to force it with positive feedback. But realize, I mean, you overshoot a little bit and you're really screwed. So. Essentially, I will never give you anything that looks like this, and you can pretty much expect nobody else will, unless you decide to do PhD work in this field. So far so good? All right.
Have you ever designed a system with positive feedback for any specific purpose?
For a practical thing?
Yeah,
No.
for practical. Okay.
Have I done it for problems in homework assignments during my PhD? Yes. Okay? This is why I draw the distinction between, do I know how to do this and would I ever do it?
Right. Yeah.
You know, I can't really off the top of my head think of a good case where I would do positive feedback as opposed to, I can make negative feedback where things just graze and come across and come back in. And the neat advantage of doing that is that I only get exactly as far out there as I want to go.
Yeah. You actually have a known
Right?
amount of
So if you overdo it, you become stable again. Okay? So that's actually something where I feel more safe on
Right.
as it goes. So, all right. So now we see why I have these segments drawn in here. Yes? And we saw that they do have to move towards each other. Okay. Now we want to deal with some other questions that come up on here. For instance, it would be nice to know, like, where is that point?
I had assumed you drew it right in the middle of the two. But
Yeah,
it really
it's
depends on where
not
the poles
guaranteed to
actually
be right
come
in the
from.
middle.
Yeah.
Right? There are times when it will be right in the middle, but it's not guaranteed to be right in the middle. Where two branches hit each other, okay, at that point you've got a double zero in essence on the bottom at that particular point. So now you're actually kind of controlled by L'Hopital's rule, so you have to take a look at the derivative to find what's going on. So if you consider the derivative with respect to S of the characteristic equation, 1 plus k g h. If I consider that and look where that goes to 0, I'll find out exactly where those points are. That's that special case where two of them collide. Now, derivative of 1 is
Zero.
0, so most people just leave that off. If you do the derivative of k times g times h and k as a constant, what can you do with that k? You can pull the k out, can't you? But then k times this derivative equals 0. Do you need k? So this is what almost everybody gives you as the rule. And I've never seen anybody explain why this rule really is. I mean, maybe if you look up a proof book, but in most books they don't tell you why that rule comes about. So hopefully this will at least give you an intuitive reason why it's there. It still really is dealing with this. It's just when you take the derivative, the 1 and the k are unimportant as it goes on. So I just take a look at the derivative of these. Now there's, I think, a slightly nicer form. Once you know n and d, g times h is n over d, right?
Yeah.
So this is also an equivalent condition, right? But what's the derivative of n of s over d of s?
Quotient rule.
That's through the quotient rules, which is?
Trivial.
I agree, but what is it?
F prime.
The top times derivative of the bottom.
Minus the derivative.
And realize it actually doesn't matter all over d squared, but realize that d squared, we're assuming it's non-zero, so I just multiply through by d squared and away it goes. Right? And you actually don't have to remember it's which one minus which one. Since they're both equal to 0, you can take it to the other side.
Yep.
You just have to find when that's true. Okay? It's exactly equivalent, but I think it's a little bit easier to do because when you write this, and you have to remember that stupid quotient rule, and then people actually divide by d squared, and it gets really kind of ugly. So I suggest that this actually is a much simpler one to remember as you go. Now that one I kind of ballparked about where it should be. If you want to calculate it exactly, just solve this. When is this equation true? For what value of s? Okay. And that will give you that exact point. Okay. Anytime it gives you something off the axis, off the real axis, don't worry, it's not an actual hit. So you only worry about the ones that are on. You plot those, that's where the collisions are. So in this case, this, and this would all be gotten from this equation. For this form right here, you'll have 2 off-axis. And they never actually get hit. They're potential hits, but they're not actually there.
When you say we get those from that, where would...
So watch. What's the numerator? Okay, if I use my simplified version here?
Yep.
Just so, because it's a lot easier algebra when we're writing it out.
Okay.
So for our thing, this is D, and this right here is N, right? So I want to take a look at when S plus Z0 times the derivative of this. Well, what's the derivative of this? You can either do chain rule, right?
Yeah, expanded.
In this case, I mean, the derivative of S on each of these, their leading coefficient is 1, so it's pretty easy if you want to do it by chain rule. Or you can just multiply it out.
Which we have.
You know, life's tough, right? So S squared plus P0 plus P1 times S plus P0 P1. All right? So if you like this one better, just take the derivative. So I get 2S plus P0 plus P1.
Yep.
All right? And that's got to be equal to n dot times d. Well, n dot is just 1 times d. I get my s squared. Well, I just get s squared plus p0 plus p1. All right, solve for s. All right. And that gives you what are called the breakaway or break-in points.
Right, and then so we'll get 2 answers, and that'll actually be our 2 spots. So.
Yeah. In this case, you potentially can get 2 answers, right? If they become complex conjugates, it's irrelevant. There's no break-in or breakouts.
So then both would be in the center in that case of the 2
Right.
points.
Yeah. So when you consider what's going on in these ones and you take a look for our larger size system that's going on, I could potentially have a large number of break-in and breakouts, right? Because I've got 4 and 7. I mean, if I took a worst case scenario as it's going, I could have plotted them all on the real axis, right? 1, 2, 3, 4, 1, 2, 3, right? So if I took those as it went, worst case scenario, I'd have here, 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 and here as we're going. So I would have breakaways, something probably like that. I'd have to actually plot it out to make sure. But you'd have something approximately like that as it's going in. So I'd have a whole bunch of them as they're going on. Yeah. So when you took a look at this one, you can see I get at least a fourth order from D.
Right.
As it's going on. But it's slightly adjusted by the end dot. So then you take either one to the other side and just solve. Find out what the value of S is. You're done. The values of S that are real that make that satisfying, where the roots are, that tells you where those breakaway or break-in points are.
Both the breakaway and break-in?
It's the points where that can happen. So it's basically where two root loci are able, or two of the branches of it are able to collide. Yeah. In theory, I could have a couple collide other spots and things like that. You know, which is why I can even go higher.
Would it be 4 and then?
Right, so I mean, theoretically, these could hit here, and those could theoretically hit. You know, as it goes on, so that would be the complex ones. But in general, you just worry about the reals, because those ones happen all the time.
How would a complex conjugate work?
It's a couple possibilities. The most common one is on something like this, and it's potentially something where there's, you know, a potential for a problem that goes on where things could collide, right? But it doesn't actually happen because the loci never hit them, right? Or you'd have to have an off-axis hit.
Yeah, I'm just trying to imagine.
It's a bifurcation point, right? Really, when you want to get down to it, that's where two of them hit together, so you get a reduction, a degeneracy within the equation.
So you're actually losing power?
Degeneracy means you're losing order, becoming a simpler system that goes on. Once they hit each other and they're exactly the same, right, it is a degenerate condition is what we call it, because you have less ability to adjust and control the system. That's the, you know, critically damped spot. But when you consider inversing that system that's going on, you've got something that looks like, you know, something over S plus A, whatever that root point is, squared.
Okay.
And the second you have that S plus A squared, you have both the behavior of S plus A and the behavior of S plus A squared. And the S plus A squared, remember, is T times whatever's in there, so it's T, E to the AT.
Oh, okay. Yeah.
And that corresponds to the degenerate or Jordan form of an eigenvalue, what are sometimes called Jordan vectors. So, yeah, we're using the same exact term that's used in the matrix form when it goes on, for the same reason. And this is kind of a little bit of a challenge. I mean, we usually don't like to see T appearing directly in the equation like that. We like it up here in the exponent.
Right. A little off topic. That reminds
Yeah.
me of the transformations for Laplace. When we just have a constant in our time equation and we take it into the S domain, like in circuits, are we supposed to treat that as a U of t attached to that constant?
Yeah, it's always because remember you turned it on at some point.
Okay. Yeah.
So we're assuming that we are dealing with, you know, in essence, right-handed systems because we were doing the Laplace transform, just the right-hand version, so 0 to infinity, which means everything is technically multiplied by U of t,
Okay.
whether you show it or not,
Gotcha.
because that just turns off the negative side of this. Otherwise, you'd have to use the bilinear one, which goes both directions.
Okay.
And it's, you know, just neater for convergence and everything else to do the other one. And it's reasonable enough for us to make the assumption that it, you know, it's turned off when we turn it on at some point. All right. So far, all right. See, lots of blank stares. You know, is it we too much math, we too little math? Where are we at? Are we remembering these type of things? I'm trying to remind you of different areas, like L'Hopital's rule, when things, you know, this is when you discover them and you get two things that are running towards zero in essence that goes on. Right? Same type of thing happens when two of these things are colliding, so you have to consider the derivative to find the root. It gets hidden.
Yeah, it's just things like that didn't occur to
Should
me.
there be a K at the?
Oh, yeah, sorry.
Okay, sorry, that's just.
Yeah. And technically it's, you know,
Yeah.
I see. Yeah. So I was being really pretty lazy when writing it, which, my point just being actually just to emphasize that
Square
that
is
square,
TAEA.
in essence, multiplies by t. And that is, if you ever go back and take a look at the degeneracy inside of eigenvalues, degenerate eigenvalues, the associated eigenvector ends up doing the same exact thing. The first one gives you that, the second one does that, and you get a, you know, t squared over 2, blah, blah, blah. All right. So, but we have a nice, fairly straightforward, I mean, albeit you have to solve another stupid polynomial to find points, but I can get the points where this can happen. If it's on the real axis, you mark it, and that's where something is going to either, in this case, break in, or if it's between two of these, it's a breakaway. But really what it's telling you is where two of them collided, and they're together for a brief instant. That's the degeneracy. They both have the same value. Right? Before they were distinct, after they're distinct. For that one instant, they have degenerated. How do we find that? Take its derivative, set it equal to 0, and we get the points. Plot those points, and away you go. All right. So far, so good? Okay. So I'll remove the more complicated one and deal with our simpler one at the moment. So now we found these segments, we found where it hits. There is a possibility, one other thing that could go on. In this case, I only had one that was different. It is fairly common that I could end up with a whole bunch that are distinct. What if I ended up having a transfer function that looked like this? Right? Let's say S plus P0 times S plus, let's just do 2. What if I had that as my KGH? No zeros. I have 2 poles. Right? Now, if they're distinct, have something like that, at minus P0 and minus P1, you can figure out where it actually goes, but how does it run to infinity now? Right? Before it was obvious when it was just one segment. And that's why I actually picked things that were different by 1, because it's easy to see why. But what happens here? Well, same thing's going to go on just as we did to calculate. You'll find there's a breakaway point, and they will run out, and they will go to infinity like that. How do I know? All right? Well, now we have to actually, again, satisfy any point on the loci has to satisfy our angle requirements. All right? So if you think about this little angle segment here and this angle segment here that's going on, right? In this particular case, it ends up being that the breakaway point is right exactly in the middle. And this goes straight up. As a result of that, there's kind of a neat simplification that goes on. This angle exactly fits what's in there. So it gives you your nice little pie segment. Right. So you can see, oh, that really does satisfy it for any value as it goes straight up.
Right.
So it would work nicely for that case. So that's got to be on it. By mirroring, the other one has to. That's how you can see it for 2. It's slightly more complicated to prove some of the higher dimensional ones, but at least once you get an indication, why does that work? What you're just trying to do is make the angles all work out to satisfy this condition.
basically when it's not in the center, we're going to have a more
When
complicated way.
well, if it's off a little bit over here, if I pick some candidate point, is this on the loci? Right? If I take a look at the angles, that angle plus this angle do not add up to pi.
Right.
But they have to. So since they don't add up to, but they have to, it cannot be on the loci. It can't be part of a branch. So we know that's not part of it. So that's really all we're doing, is we're finding out where is it satisfied. Make sense? So we can take a look. Whenever these happen, they might be a little bit shifted one way or the other. If I put another pole in, right, it would add a little bit of an angle to things, right? But what if I put another pole 0 combo? Right? Well, this one's just going to run off to the end here. You kind of expect these are still going to go there.
Right, it shouldn't affect.
But remember, it's this angle and that angle, the difference of them. They're not exactly on, right? As a matter of fact, this being a little bit smaller than that one, right, means that I've got a little bit too much angle, right? This is the zero's angle. Let me just call that z. This is 0 plus some little amount epsilon. It was a little bit too big. So I need to make sure this whole thing gets a little bit smaller, right? So these ones have to shrink a little. Right? Because before they perfectly made pi, now they've got to be pi minus epsilon to account for that. The only way you can do it, if you shifted this over a little bit, that angle goes down a little, and this angle goes down a little. Right? So as long as I adjust it such that this plus that is equal to the epsilon, I'm good, right?
Yeah.
That make sense? So that means it's still got to do the same thing, it just does it shifted over. The whole thing, instead of going up like that, it can still break away wherever it wants, but it's got to follow up a slightly shifted route where the asymptote is. So far, so good?
Yeah.
Makes sense as an idea? Now, if you think about this, if you kind of think of these like charges, it doesn't perfectly work, but it kind of gives you a good feel for it. Imagine x's are plus and zeros are minus, or you can flip them, I really don't care. Right? It kind of gives you the right idea, right? The pluses want to go to the minuses as it goes on. And if there's a plus here and a minus here, you're kind of on the plus side, so it'll repulse them a little and it shoves them the other way.
Yeah.
Does that make sense? If you had flipped these, you would be subtracting this angle, which is big, and adding this angle, which is small. So you'd have a little minus epsilon. So it'd have to come this way. It'd be attracted to that and pull over this side. So it at least gives you an intuitive feel
Yeah.
for what's going to happen. So when you generally look at these, and this is how I actually do when I look at them when they're coming in, right? I take a look at this and I go, okay, the x is the closest thing. It's going to want to push these ones away. So it's going to come off this way. It's got to, because this one's dominating the push of what's going on. There are exact rules to calculate this, but again, right now I just need you to get an intuitive feel so you can sketch it. So this one dominates. If that had been a 0, it would have actually pulled it and they would have come this way and then had to pull back in. Makes sense kind of behavior-wise? So if you think of it in that way, it's not always perfectly that, but it's pretty darn close. It gives you a pretty good sense of what's going on. All right? So that's why I kind of drew them coming off here, is because the closest was an X. And this one dominates that, and that one right here, there's nothing to block it, so it also adds a little more. So it's going to even push it harder.
Gotcha.
No? Good?
But like the harder one though, where those were reversed, would it, like you were saying, that angle?
Why reverse these two?
Right, right. And so your poles off the real axis are
Would be
actually,
even more twisted,
right,
right? They'd be more pushed away as it goes because I'd have more X's right there,
closer. Yeah. Okay.
right? Now what's really happening is the angle,
It's just
right?
being
You've got,
shifted.
you know, the bigger angles close in, and so you have to account for more of those, so you have to adjust the other one more. But, all right, good?
Yep.
Okay, so we take this now, we say, okay, great, we see when it was in excess of 1, it ran this way. When there was 2 extra poles, it did this kind of a thing. Right? What do you think is going to happen when there's 3 extra poles?
I don't know. Probably have 3 lines going in some sort
Well, let's think what's happening here, right? There's 3 poles, right? Assume there's no zeros, 3 poles. Where must the root loci go?
Go all the way to infinity to the left.
The odd numbers, right? So it defines these ones, which means one's running off to infinity this way. These two have to come together and hit, but this is now repulsing it, and there's no balance.
Oh.
Right? So what's going to happen with those is it's going to bend away. And what it's going to actually bend away at is, we'll calculate the exact point, these angles, it ends up going exact opposite. Again, think like charges. If I stuck 3 protons right next to each other, right? Or say 3 electrons, I shoved them right next to each other and then released, what would happen?
Fire
Fly
away.
away.
They'd fire away in which way?
Away from each other.
Away from each other to disperse the charge as best as possible.
Yeah.
So you would take a plane and you divide it into 3 equal pieces.
Yeah.
Yeah.
I mean, that's the best way they can get the charge to the lowest point fastest. Well, that's exactly what happens here. Right? 120 degrees, 120 degrees, 120 degrees. But notice, this is kind of my anchoring point as it goes on here. Right? So thinking, imagine I'm confined to a plane. Right? In each sense, that's kind of what happened here, isn't it? They went away as best they could.
Yeah.
Here, there's only one, and it just runs out to infinity. So if there's ever an odd, I seem to always have one that runs out to infinity, don't I? Right along the real axis. And then the other ones distribute them evenly around the plane.
Right.
Does that make sense? That's exactly what goes on. So all we have to do is take the plane, divide it evenly into pieces. And so they give you this lovely little formula, 2k plus 1 divided by the number of poles minus the number of zeros times pi. And that's the angle, or actually I guess I should use n, right? For some integer, right?
Yeah.
And if you stick n equals 0, n equals 1, all the way up to, you know, p minus z, minus 1 technically. If you go through every possible one up to the number of extra poles, right? P minus z, that's the number of extra poles.
Yeah.
Right? The 2 times it, if you just think the 2 times it part, that gives you 2 pi. So 2 pi over p minus z just evenly divides the angles up. So 2n p minus z times pi, that's the even division of the angles. This extra plus 1 is the phase shift.
Right.
And it accounts for the fact that this right here is 60 degrees, right? Whereas this one right here, it starts at 90. This one, it starts at 180, if you want to think of it in degree terms. Right? That's what this one is guaranteeing you start out. If there's 2 of them extra, 1 over 2 times pi is
2 over pi over 2.
pi over 2, which is 90 degrees. So if there's 2 extra, it just gives you what's the starting angle. So So that's what the +1 does. So this gives you the starting angle, and this gives you the distribution.
Okay.
But I argue to you, you don't even need to worry about that. You can actually do this intuitively without it. Just think about it. If I told you there was 4 of these extra poles, 4 of them, they're evenly split, so they have to be every pi/2, right? Can any of them be running off to infinity? No, because
They shoot straight up and down.
the segments would have to lie like that,
You just have 2 lines going.
right? So, but they have to be evenly distributed.
Right.
And they have to be pi/2 between them. We said they evenly spread out,
So you
and I
got
can't have anything on here, and it's got to be symmetric. So the only way I can do it is that way. All right? 45 or pi/4, whichever you want to think of, and between them it's pi/2. Between each estimate. It's got to be. It's the only way to be evenly distributed, symmetric, right?
And not running off to. Okay.
Yeah, and not running down this axis.
Cool. I'm very comfortable with that.
Yeah.
So how do you get the one that you said where it goes unstable, but then it comes back and goes stable again?
So what you do is you adjust these. See how the angle of departure here? If I set these up so that this is going like that, imagine I have, you know, an asymptote that's over here, but I force the angle of departure to come out, and then it's got to come back in. Right? So if I force the angle of departure from my poles, there's some other collection of stuff over here, but the asymptote is running like this. I can force it so it goes out and has to come back. So you just have to control this angle here. So it's initially repulsed, but ends up back at this point. Which means you'd have to have some X's here, but some strong zero effect, which pulls everything back in line. Once you get far enough away, the
From
distance
the
becomes
X.
pretty insignificant.
And then, yeah, and then
Right?
zeros
So
take-
that'll kind of pull it back in the end. Yeah, so I would need that and then some strong zero action out here. You know, initial strong pull, some strong zero. Make sense?
Yeah.
All right, so if you see stuff like that, then you go, oh, you know, I've just pushed myself over the boundary just a little. So far, so good?
They'd either have to be pretty close to the measurement
Yeah, you know,
axis.
yeah, that's.
So that's already kind of.
But think about this in real life. If I've got an airplane and I want to, in order to do a fast turn, I've got to go just unstable,
Right.
and then bring it back in. If you're not close to unstable to begin with, it's going to take you a while to make yourself unstable,
Right. And then that's not exactly.
which is a
faster.
delay in how fast you can turn.
Okay.
So I've got to be pretty darn close to unstable, but just right on that kind of hairy edge. Then you just push over and just wow, and then come back.
Oh,
Okay.
really fine.
So yeah, I admit you're kind of living on the edge there.
That's when it goes a little
That is,
That's it.
but that's what you want to do. That's the whole point of it. You're saying, hey, I can keep it stable even in that kind of marginal zone there, but I can use the slightly unstable part to make me turn really quick or get whatever performance behavior I want really quick.
Yeah. Oh, that's good.
Yeah.
The pi/2 one, they crash together and then go off along the asymptote that you drew.
All right, what's that?
No, pi/2 one you drew here,
Yeah.
they crash. They go
Well, not
together
necessarily.
and then-
These ones right here, these will come, and in all likelihood, they'll run like this, and these ones will in all likelihood run like that. Because remember, they kind
they
of
co-crash
repulse
and then
each
they go
other.
off, right?
Yeah. So now you figured out the angles. The only other thing you need to find out is the center.
Right.
Okay? Now, it's symmetric, so what's the imaginary value?
0.
0. It's got to be on the real axis. Right? To find its location on the real axis, you just find the center of mass.
Oh, we can use just regular center mass
It's
equation.
poles, the actual pole values minus the 0 values.
Oh.
Consider, you know, this is again kind of, I guess it would be better rather than center of mass, like center of charge, if you wanted, you know, as kind of a, maybe a better descriptor of what's going on there. So, but you just add them up wherever they are. You only care about the real components that go on. So even if I've got off-axis ones as complex conjugate pairs, I get twice the real value, but the imaginary values cancel, so who cares? Right? So you just add them all up, find the center of that, kind of quote-unquote mass or charge mass, some's positive, some's negative. Wherever that is, boom, that's the center of those asymptotes. At that point, you can draw the asymptotes. Where is it ultimately going to? You can center them by just finding center of mass. You can find the breakaway points by saying the derivative equal to 0. And you can find the segments. Right? The only thing I haven't told you how to do is once you take a look at this, right? We've said, you just want them on the left-hand side. But what if, let's say I want to pick this point here, and I say I want to operate right on that edge. What's the value of k that gets me there? Remember I told you we had two forms. I've been using this one a lot, haven't I? Now you use this one. The root locus, is satisfied on here. Well, what this means is if you calculate for that particular value of s, pick your point, that gives you a particular value of s, right? Say S0, whatever you want to call that point. This right here tells you that the magnitude of GH at any point, right, has to be equal to 1 over k, assuming k is positive. And that's what we'll typically do is pick positive gains. So I've just rewritten this one slightly.
Yeah.
But that means it has to, in particular, work for evaluating at s equals S0. Evaluate that at S0, take its magnitude, that is 1 over k. It's got to be. It's the only way it could be on there. But that means that is the value of k that will get you to that point. So you typically use this one to draw the thing, and then you use this one to figure out what got me there. Right? And I usually pick this point because I don't want to pick this point up here because I have to go unstable first to get there. That's why you kind of want to see what the whole thing looks like. Make sense? Awesome. That's the basis of it, right? So I can now sketch it, and then I can use it to find out what value of k got me there. And you just set your k equal to that, and you're done. That is the basic root locus technique. Draw the picture, find the point that meets your requirements, use this formula to find out, what value of k got me to that good spot. Done. Make sense? That's one way to find k. That's the easy way. So, yeah, I know, most people are like, I never want to see this again. Hopefully, I would encourage you this. Try drawing a few of them, right? The more you draw them, the more it becomes clear. When somebody does it up here, right, your mind doesn't track as well.
Yeah.
As it's going on. You have to kind of run through an example. I'm past time. So, maybe next time we'll just do some examples. Because we do have some people who are kind of, going to be taking the test on Friday and stuff because they have internships and things. So we'll do some examples of these ones. And then we'll, maybe just to be fair to everybody, I'll pick nothing past root loci to be on the final itself. And then next week will be free fun. I highly encourage you to pay attention to it. We'll go into the matrix stuff to get better solution techniques and things. But we'll go through this one. So we'll do some examples just of solving these next time.
Okay.
Thank you.
Good?
Yep.
Yeah, we tried to do your practice.